Okay, so what we where we stopped yesterday was let me go. We were discussing about the ash formation mechanism, ash deposition, and within ash deposition, mainly fouling and slagging, how these are defined, where do they take place, and what are the different ways of controlling them, the potential ways of controlling them. So we stopped at that point, and so this is the slide where we stopped. By the way, all these presentations are now available. What we discussed this morning with Professor Day is that if you give me your email address, we'll be opening up an electronic repository, and I will be placing the presentations there for you to download either on the morning or any time later. Okay. So share with me your best email address, and then we'll open up the repository and all those. And but all the presentations from today, those are already available. Okay. So we were discussing how the slagging and the fouling occurs. But then more specifically, this is around this point we stopped, where we were looking at how you can analyze the deposits and then find out what's the composition of the deposits. The intention is, if we know the composition of the deposits, then we should be able to form some impression of how they formed, at what temperature did they liquefy or became liquid, became molten, etc. And therefore, that will hopefully give us some strategies to avoid that temperature. So that's the idea. So one of the ways to look at the deposits, or in fact the ash before the deposits are formed, you can burn the ash at low temperature, burn the coal at low temperature, around 600 degrees or so. So nothing vaporizes from the coal except the combustion of the char. So what stays is all the pristine components of ash, or the pristine components of minerals, which get converted into ash, as we mentioned. Then that ash, you can subject it to scanning electron microscopy, and then you can interrogate the software of the SEM through what we call the energy dispersive X-ray spectroscopy, EDX, and then find out at a particular location what's the composition of it. So this is just an example here. It is showing us that at that location, it has this much oxygen, this much carbon, this much magnesium, nitrogen, aluminum, silicon, sulfur, calcium, etc. And the software itself, based on its database, can actually give you the mass percentages, which will then allow you to calculate the approximate formula for it, chemical formula for it. Okay. So if you do that, if you find out the approximate chemical formula, then you can look in the literature, or you can use softwares, look at the phase diagrams, and then see at what temperatures that this kind of compounds melt. So that gives an approximate idea. But so there are certain softwares these days available. As I mentioned, one is HSC Chemistry. It has developed quite significantly. But better than that is a software called FactSage, FactSage, So that is commercially available, academic licenses are available. So all it needs is to give the input of the elemental composition, such as the ones that you can get from here, and give also the condition, whether it is oxidizing. If it is oxidizing, how much additional excess oxygen, what is the temperature, what other gases are there. It does the equilibrium calculations by itself, and then can tell you, okay, this is the compound that's the most likely to form at that temperature under that environment, and this is the liquidus temperature, the melting temperature of it. So it's not absolutely perfect, but it is getting perfected every year as users provide their feedback to the software developers. They gradually go on perfecting it. So it's like any process simulation package. For example, Aspen Plus, many of you may have used Aspen Plus, is that right? So the predictions from the software is as good as the database that it uses. Okay. If its internal database is not good, if the internal property tables that it uses for the equilibrium constants, then the equilibrium calculations that it will perform to give you the products will not be correct either. So it's a matter of time before these databases get more and more developed, and usually the users drive it. So for example, whenever we use FactSage, and it gives us certain indication of a compound, but we do not find that compound through other means, through other analysis means, other means of analysis, such as X-ray diffraction, etc., we then tell them that, look, we do not have it, we do not find it. They then go on tweaking. So that's one way. But the softwares these days are very, very good these days. So a lot of the, so 15, 20 years ago, all of these calculations used to be done by hand, manually. Now, no one does it. But you really need to know the basics behind it, though, in order to ensure that the results that the software churns you out is actually a realistic one. So never to take them for granted. Okay? But this is an example. So say we talked about fouling and slagging yesterday inside the furnace. And if you have a piece of fouled deposit, you mount it in the SCM, you analyze it through scanning electron microscopy and interrogate the composition through EDX, feed that into the software, that will tell you what the liquid temperature is, and that's the way to go. And that then can feed into the operational strategy. Tell the operator that please ensure that temperature doesn't exceed this much during your operation. If it tends to exceed, have control measures. So that's the importance of this type of chemical analysis, coupled with predictive calculations done using the softwares. Does anyone have any question so far? Sorry? Exactly. And therefore, it will increase the fouling. And potentially, it can go into slagging mode as well. Yeah. Excellent question. So, when you do the EDX using scanning electron microscopy, it doesn't discriminate between crystalline compound or amorphous compound. It just finds out what element it is depending on how many electrons it has been able to bombard out being detected by the detector. So it's not discriminating on the basis of crystalline compound or amorphous compound, which X-ray diffraction does. So whatever you get from here is whatever is there, right? Amorphous, crystalline, etc. And the beauty of it is that you can then calculate the approximate formula for that composition at that point, approximate formula. X-ray diffraction is slightly different, as you rightly pointed out. You can also subject this particular deposit. You can either power, you have to grind it to a certain size and then subject it to X-ray diffraction. X-ray diffraction will give you the more or less the exact compound, matching it with its internal database only if the compound is crystalline. But if the compound is not crystalline, it will not give you a sharp pick. It will just give you a big blob like that. And if it is not a sharp pick, you will not be X-ray diffraction. The software will not tell you what the compound is. So that also leads to another question, is that what makes a compound amorphous or crystalline? Right? So does anybody want to share wisdom about, opinion about that? Correct. So did everyone hear that? I think the basis, so you have taken us to the right direction. If you take certain amount of ash, maybe to start with, the majority of them are amorphous. If you subject it to heating, and as you said, slow heating essentially I think you meant prolonged heating for a long time, then the structure will eventually change from amorphous to crystalline. So that's something that what is currently done is very well developed technique. It's called high temperature X-ray diffraction. So what you can do is, you can take a sample, put it inside the sample holder, and then heat it, monitor its temperature against time, give it as much time as you need, and then keep on taking the diffractograms. You will see that initially you are seeing a blob. After 5 minutes, you are seeing a smaller blob, then a smaller one, and then all of a sudden a peak will appear. This is something that we routinely do when we do the fuel cell research, particularly the solid oxide fuel cell research, and I think I will be talking a little bit about that next week. But that's the important thing, that is the temperature, exposure to temperature and over a longer period of time, that usually makes these sort of solid materials change from amorphous to crystalline. So the X-ray diffraction and the EDX are complementary techniques. Sometimes it is good to have it, do the calculations, but it's also good to then verify it through the complementary X-ray diffraction. The reason behind that is that if a compound is crystalline, it's very, very difficult to change it, the character of it, because it has become so well structured. But if it is amorphous, so the classic example is if you take a certain amount of ash, and those who will be doing fluidized bed gasification or combustion research, you will face that music. As you said, temperature over a prolonged period of time gives you more crystalline compounds. And if crystalline agglomerates form, then it's very, very difficult to break them. I will talk about that in the second half of today when we move to gasification. So coming back to this, so we have got this sort of composition, and then we know how we can analyze that in conjunction with the software to get a liquid dust indication of the liquid dust temperature, and that has operational significance. Okay. The other complementary technique is X-ray mapping. It's more to know. It's not necessary to have this sort of analysis on a day-to-day plant operation purposes, not at all. But if you see that a plant has been facing problems of deposition, fouling or slagging over a prolonged period of time, and no matter how you take mitigation measures, the problems are still persisting, then sometimes it's better to go into the X-ray mapping kind of thing. So to see over the entire area of an agglomerate or entire area of a fouled section, what elements are there. So you can, again, it's a scanning electron microscopy based technique, but you need slightly different software and different hardware as well. And you can literally specify which elements you would be preferentially looking for. So it needs a little bit more specialized knowledge. And then it will tell you, okay, if I have this sort of color coding, one color for calcium, another color for iron, another color for sodium, another color for other elements, etc., it will actually give you this sort of colorful figures. So in this one, for example, all the black spots, these are clearly showing that there is no calcium, iron, silicon, etc. in those black spots at all. But wherever they are, for different, you can see at that particular point, it's actually a combination of calcium, iron, and silicon. Whereas in some of the reddish ones, it's predominantly that one. So it's a little bit more sophisticated. It requires a fair bit more experienced, fair bit more experience, and to essentially to interpret what these ones mean. What these ones mean eventually is, though, that when you map it, you can actually see how widespread these are. Are all these elements present equally, more or less, everywhere, or are they present only in discrete places? So that's the beauty of mapping over ADX that I showed in the previous slide. Okay? Very, very time consuming. So this will take, say, around back in 1997, 98 when we started, this sort of maps used to take overnight. So we load it at 8 o'clock in the evening, and then you come back next morning around 6-ish, it will be ready. But now it takes about half an hour or 1 hour, depending on how many elements you are asking it to map, because it maps entirely from one side to the other. And if you have more samples there, then it becomes a little bit more time consuming. But these are all automated process. As long as you set it up, 30, 40 samples in one go, come back and then get the results. Then comes the actual work, the interpretation of it, and how that interpretation is translated into the operational strategy. Okay. So that's just one example of X-ray mapping, and I think I will talk a little bit more about it when we share my knowledge of CFBC and gasifier operation later. Yesterday I was talking that I was telling everyone that, yeah. Which ones? On the sides. So black spots in this case are not indicated by any of this one side? Okay, that's a good question. You have to mount it on something, the agglomerate or the foul deposit. So this is mounted on carbon tape. So and that's where nothing is there. So black tape, black location, black color in this instance is showing that it's the substrate on which this deposit is mounted. Very good. Yeah. What do you think? Why do you feel that it's relevant? Extreme mappings, unless they are coupled with EDX, will not give you the concentration. This will only show you what is present along with what else. So it is showing that in some cases, calcium and iron and silicon are coexisting at the same spot, but it is not telling you how much calcium, how much iron, how much silicon. You can do that too. You can ask the software to, at the same time, to give you those numbers. It will do it. Whether those numbers will be absolutely correct or not, that will depend on its own database and your experience. Okay? It's possible, take longer. But the way I have showed it, it's just showing the coexistence of it or non-coexistence of it. Good, very good question. Any other question from anyone? These are all semi-quantitative. So EDX is the simplest semi-quantitative method. Again, when you do the EDX, because it is detecting the elements and the concentration of the elements by counting how many electrons it has been able to dislodge from the deposit towards the detector. Now, not all electrons may have gone towards the detector. They have gone tangentially outwards. So, and also, it also depends on how many electrons it has been able to dislodge, which means what the electron volt that you have used, whether it is 10 or 15 or 20. If you do too much, then it will dislodge everything and you will not get much. The detector will be simply saturated. So the detector will not be giving you anything, any meaningful information. So to answer your question, it's again a compromise, a balance that you need to strike. But very quickly you can find out, the first thing that the students do is they run the same sample at different electron volts and then see what they are getting. And from there, very quickly establish, okay, I will stick to 15 electron volts in this instance for this type of samples. Because some elements are very easy to dislodge, and they move around very fast. I mean, chlorine, for example, is one. If you apply too much of a voltage, it will simply be moving from one place of the deposit to the other place, and you will not be getting a representative sample of it, a representative indication of it. So to answer your question, is all of these techniques are semi-quantitative in the sense that everything depends on what voltage you will be using. No one can tell that this precisely. Absolutely. You have to give the conditions. Yes, that's right. I mean, when I review any papers, I tell, okay, give me the condition. Not for me to check, but for others to then use it. So you need to be absolutely transparent in telling. There is no right or absolutely wrong condition in here. Only thing is very, very important, particularly who the research students are. It's very important that you tell everything clearly so that others are able to reproduce those results or say that, no, look, this had some problems. let's fix it, let's develop something more correct. That's how research is. I mean, research is essentially a combination of two words, re and search, right? So everything that I am doing today, 5, 10 years later, this gentleman can tell that, look, you are not quite right in this and this aspects, so we are improving it. That's how research progresses. So nothing is absolutely perfect at any point of time, but it gives you an indication. But your task is to report everything transparently. So this, no. These are sharp picks. And by comparing against the library, you can tell the area underneath each corresponds to what percent. Just as you do in your GC, right? You get the location, and the location tells you, okay, this is my molecule, and the area under that pick tells you how much it is, compared against the baseline standards that you have calibrated the machine with. So see, if you ask a question, so many things come out. Because otherwise I will be just blabbering about what I know. So it's best to start asking questions. And so those who did not ask any questions, today is your turn. Okay. And those who ask questions, they will keep on asking questions anyway, and they'll be appreciated. Okay. So where am I? Okay, here. So yesterday I also told that calcium, sodium, magnesium, and iron, they actually create problems. Silicon and aluminum, or their oxides, on their own they are not problematic. But as soon as the other four, the compounds of other four elements are present in the matrix, then you start having the lower temperature compounds, and there are all sorts of other problems. So calcium is actually very unique in that, from that perspective. So this is some experimental data reported by Rask, and the reference is given in the last slide of this presentation. So what it shows in here, the bottom one, is the x-axis is percentage calcium oxide in the mix of that sample, and the y-axis is the temperature. So what it is showing is that as the calcium content increases, the sample becomes more and more liquid. It becomes liquid at lesser and lesser temperature. That's why you have a drop. But beyond a certain, it's a drop. But beyond that particular point, for that sample, beyond that particular point, as the calcium content increases, its temperature increases. That means for that sample to become liquid, now you will need much higher temperature, which is good. That means in the normal operating temperature zone, if you have a lot of calcium, then it will not melt, which is fine. And similarly, this is another set of graph which is taken for a system consisting of these two are fine, but these two. It is very, very confusing in here, as you can see. Initially it drops, then it goes up, then it drops, and it goes up. So the message that we are trying to give from in here is that the presence of the calcium and iron, and also similar observation you will see from sodium's and magnesium's presence, is that they really start giving an unpredictable character to the deposits. Sometimes it will drop, sometimes it will go up, sometimes it will stabilize. So So what does that mean to the researcher or to the plant operator? It basically tells you that we really need to be very, very careful when dealing with this particular coal, when that has a lot of calcium or less calcium, or a lot of sodium, iron, etc. If that is there, then the best thing is to find out what is the safest temperature zone to operate and what temperature zone to avoid. And that's what the engineers eventually will need to know. The scientists and the researchers, you can provide that information, and you can tell them that this is my judgment based on my old analytical work that I have done, complemented with the thermodynamic calculations, software-based calculations. Avoid going to a temperature beyond this. So that's how I try to interpret this sort of information. Okay? There is absolutely no point in trying to interpret how much the temperature changes because of calcium oxide changing from this value to this value. Because if you have another element in its matrix, the character will be different. As long as you know it, and as long as you then define, absolutely surely, categorically define that this is the temperature beyond which the composition will be, the character of the deposit will be unpredictable, that's the most important information for the operators. These days, you can actually generate this sort of graphs in here, liquidus temperature, when you have multiple, when you have compounds of multiple elements. So, for example, you have run a fluidized bed of some description. You are facing problems. You take the samples out. You don't know why exactly it has created that problem. Roughly, you know that, yeah, maybe I have gone to too high a temperature, but what could I have done? What exactly has happened? Take the sample out, analyze it by EDX, get the composition, put it into the software, and develop this sort of graphs. What this sort of graphs will tell you, and on the x-axis in the graphs, you can ask the software, or you can draw it by yourself from these, from the EDX results. You can have different x-axis in here. So, sodium oxide, for example, or iron oxide, or magnesium oxide, whatever you want to. The bottom line is, it will give you a map of where what is forming. So, this temperature in this region, the compound that the software is telling you, based on your input, the compound that is existing is olivine. Look at the database now, openly available. You see at what temperature olivine forms or melts. So you then get that information from there. The software also will tell you in this zone between that temperature and this oxide, calcium oxide level, and this calcium oxide level, you will be getting the magnesite, the spinel structured magnesite. And then you look at the database, and then you find out what temperature it melts. Your sample must have had experienced that temperature, otherwise it would not have predicted or given you that particular compound. So even if you run your combustor or gasifier, judging by the indications given by your thermocouple, that I am operating only around 800 degrees or 850 degrees, that may not be right. Somehow the particles have experienced very high temperature and has given rise to this. How can a particle get exposed to very high temperature when you know you are not running your combustor at that high temperature? As I said yesterday, is the combustion of the volatiles, right? The 5 different stages when you subject a coal particle, drying, pyrolysis, combustion of the volatiles, ignition of the char, combustion of the char. That volatiles are very, very strongly energetic gas. They can give you temperatures, very high temperatures, very high heat release momentarily, which will never be able to be detected by any thermocouples that you insert. The reaction time, not reaction time, I mean the sensitivity of the thermocouples are not that fast. Okay? So, it will actually tell you this sort of information generated by your scanning electron microscopy based analysis complemented with calculations provide you lots of mechanistic insights. That's the point I'm trying to make. Yeah. Yeah, that's right. So, if you make the assumption that as calcium oxide increases by 10%, everything else uniformly decreases by 10%, that's one scenario, right? But there is absolutely no guarantee that everything else decreases by 10%. Some may decrease by more than 10%, some may decrease by less than 10%. There the situation will be different. So, the point I am trying to make is that this will give you some kind of mechanistic insight, some kind of information, some kind of information to make you a judgment call, but this will not be the absolutely correct call that you will be able to make. There are a lot more than this over there. But at the end of the day, what really matters? What really matters is, are you able to run your plant without problem for a long period of time? At the very least, what it is categorically telling you, what temperature zone to avoid. And if you stay below that, that's it. Everything else then becomes part of the knowledge base, but at least you are getting your objective fulfilled in the sense that your plant is operating, your boiler will be operating, your fluidized bed will be operating to the maximum desired time. But you are absolutely right. So, you can actually say you can take a sample of silicon oxide, aluminum oxide, iron oxide, calcium oxide, and magnesium oxide, and say sodium carbonate. You mix them in certain proportion, you mix them into another proportion, if this, another proportion like that, melt them to the ash fusion furnace, as I showed the other yesterday, those cones, you will see they all will melt at distinctly different temperatures. You can find that easily. These days it's really, really easy. So say for example, you have a starting composition. In the second composition, you increase calcium oxide by 10% and reduce everything else by 10%. And the third sample, you increase calcium oxide by 10%, but reduce the others by in different ratios. You will get different series of results from which you should be able to draw this type of graphs. So eventually, this will be part of the research thesis. But what's the practical implication of that research thesis? Is to come up with the operational strategy. One line operational strategy coming out from your 50-page worth of experiments, analysis, predictions, everything. But that's what is important, right? It's a solid backup that you are producing behind that one line of practical implication containing directive for the operator. Right? Okay, so you have taken a foul deposit. You have measured its composition, elemental, through EDX, semi-quantitative measurement. You can then put it into the software, and ask the software to give you the predicted compounds as a function of different temperatures, 1100, 1150, 11, whatever temperatures. So it will give you the names of those compounds. It will give you this type of, sorry. Okay. So it will give you, exactly it will give you this kind of figure. It will plot upon your direction. It will plot as a percentage of calcium oxide on the x-axis, on the y-axis as a function of temperature, what compounds are forming. In this case, it is telling you that olivine is forming, and forming in this manner. I mean, in this zone, there will be nothing except olivine. In this zone, there will be nothing other than magnetite. So it's just like the phase diagrams or the ternary diagrams that we know of. It will give you that information. So if this is the compound that has formed, then your sample must have gone between this temperature, must have experienced a temperature range between here and here. Otherwise, it would not have formed. And these databases are now very well defined. Only if it is crystalline through X-ray diffraction. Otherwise not. So the best thing is to do the EDX, get the semi-quantitative elemental composition, put it, doesn't matter if it's amorphous or crystalline, take a complementary measurement with X-ray diffraction, and then check that yes, it matches, so I am on the right track, put it onto the phase diagram, and find out. Yeah. Sorry, say again. So what are volatiles? Then methane. Methane is about 52 megajoules per kilogram. Over 50 megajoules per kilogram, I can't recall. Enormous amount, it's a tiny amount of methane. And hydrogen, right? So these all, when volatiles burn, means these combustible constituents are burning. So just imagine what should be the adiabatic flame temperature that they will be resulting in. That's how. Right? But it's a good question though. These are computer generated. Yeah, so what you do is you first do the EDX, get the elemental compositions, put that in the softwares, and then ask the software to calculate the proportion of every possible compound. Yeah, even though you do not, you wouldn't specify olivine or martensite or whatever, but it will do it. Based on the equilibrium constant values that it has inside its database, and it will actually draw precisely this. So if you can ask it to draw it, it's all equilibrium calculations, all equilibrium calculations. So there lies another side of the story. Equilibrium calculation. Correct. Yeah, exactly. And that's the message that I want to give to the research students, that you really need to know how they have calculated it. Otherwise, it will just be a number. It can be garbage in, garbage out, right? But you really have to know how it is doing the calculations. I know it is doing the equilibrium calculations. In order to do the equilibrium calculations, it will need the equilibrium constant for that particular reaction or reactions. Does it have it? In more than 100%, I mean 100% probability they have it, because otherwise they wouldn't sell it. And these equilibrium constants are now pretty well established. You can do it by yourself, but then this is a lot less time consuming. You can verify some of the calculations. For example, you can subject this to extra diffraction. If you see a good olivine peak, you know that, yes, the software is predicting olivine. I am also seeing olivine. So there are ways to cross-check it, and you should definitely cross-check it. Otherwise, it will not be a philosophical contribution to the state of the art, as is required for PhD or for masters, for example. But you can cross-check it, and you should cross-check it. Correct. Temperature, atmosphere reducing versus oxidizing. How reducing? Is it, because reducing means substoichiometric, right? Now, is it only 0.3 stoichiometric ratio, or 0.2, or 0.9? Still, it will be all reducing. That also is important to know. That also is very, very important to know. So that, and what else is there inside the composition? So this is a very simple one. The top curve is for a 4-component system. The bottom one is, the bottom one is, I'm not sure, I'll have to check, is what other components are there. My only purpose for giving this sort of figures in here is to let you know, let all of you know, how the composition, what the variables are, and how these things can be utilized to make you, to arrive at an educated judgment, nothing else. There could be whole range of possibilities. If in this matrix of this deposit, if you also have a sodium compound, the curve, the shape of the curve will be different. But the good thing is, this can be done. This is bread and butter of the PhD students' work. Fascinating. You love to go into the details of it, find it, but never lose sight of the bottom line, the take-it, conservative, final, practical implication directive for the user, for the engineers. They may not have the knowledge as you may have. Any other question? But the volatiles are there next to almost all the particles, right? So, okay, so it's a good point that you're alluding to, which warrants some discussion. Say you have a reactor of this diameter, right? And you have inserted a thermocouple here, which goes inside, and then you have an indication in here. Thermocouple is reading something which you are noting, or the data logger is noting. But what actually the thermocouple is measuring? Is it measuring the particle's temperature, or is it measuring the temperature of the void? Who knows? Sometimes it may be measuring the particle temperature when the particle is very, very close to the tip of it. Sometimes it may be measuring the temperature of the void, I mean of the gas that's sweeping past it. So you really need to know where you have put the thermocouple's tip, and that it is kept quite clean all the time, not shrouded by a whole range of materials protecting it from giving the right signal. So, as a rule of thumb, if the gas temp, in most cases, a thermocouple in this type of situation, in most cases, gives you the gas temperature, the bulk gas temperature. In a fluidized bed, burning char particles, their temperatures are easily 200 to 250 degrees centigrade higher than the gas temperatures indicated by the thermocouples. That is very well established. People have actually measured the particle temperature. You will see papers. One of my students, she worked on oxyfuel fluidized bed with large particles. So she deliberately took large particles about 6 millimeter, 8 millimeter, etc., inserted thermocouple inside that, very fine thermocouples, platinum rhodium ones, because these can be very, very thin. The K-type thermocouples are not all that thin, so you can't enter. And then measured the center temperature against the gas temperature which is on the surface of it. That student was not the first one doing it. Before that, others have also done it. In her case, it was good that this was for a brown coal, which has a lot more volatiles than the black or the bituminous coals or the sub-bituminous coals. So that's why she did it. And also her reacting environment was different. So the point I'm trying to make is that the particle's temperature can easily be a lot higher than that, purely because of the volatiles that are continuously emitted from the particles. And as its temperature goes higher and higher, as I said before, it will try to emit even more volatiles than that approximate 900 degrees 7-minute volatile content. So it is, nothing is absolutely black and white, absolutely correct. I mean absolutely sacrosanct. You really need to know the basis of everything in order to interpret the result that you are getting. And only you can do it with those who are doing all the experiments. But as long as you know it, that's fine. So what's also happening in here is that as the volatiles are released from inside the matrix of it, sometimes the volatiles are also burning inside. By the time the volatiles have gone outside, unless a fresh batch of oxygen coming in, it's a reducing environment and endothermic reaction will start take place. So even in oxyfuel combustion case, where we all say that it's a highly concentrated form of oxygen that we are giving, you will see that near the vicinity of the particle, you actually have a reducing environment creating an endothermic reaction and reducing temperature there. But inside, whether the volatiles have burnt, consuming the oxygen, that has resulted in a higher temperature, that has resulted in the particle's temperature. In situ within the particle. And the consequence of that is, because of that, the minerals inside the particle are experiencing higher temperatures. And they can then undergo all sorts of interactions, all sorts of reactions. Yesterday there was a question about that. So it may be counterintuitive, but actually that's what it is. So the fluidized bed that you are building, you can do that experience there. It will be good size. All you have to do is to make some nice round, not round, large particles, and then introduce thermocouples inside them, each of them, maybe 3 or 4 particles at a time, and then fluidize and then slowly increase its temperature, and then you would monitor its temperature, its core temperature, the particle temperature, how it shoots. Even though your thermocouple temperature in the bed, in the bulk, is giving you a lot less. Entrained flow gasification, that's a different scenario though, because here we are doing all the calculations, all the discussions centered around combustion. Whereas in entrained flow gasification, it's a highly reducing environment, much smaller particles, which is different. So maybe let's have it for a discussion when we talk about entrained flow gasification in the second half. Getting bored? Okay. Okay. Any other question from anyone? Yes. Yes. South Africa, yes. Have a wider choice of, yeah. Yeah, but okay. So let me give you an example. BHA, a long time ago in the early 70s, before I finished my school, they were supplying boiler of Russian design and Czechoslovakian design, Czech design and Russian design. Then slowly they moved away from that. Combustion engineering, CE boilers came in. Then BHL now has its own design and all. And these designs have all resulted from accumulated experience over the usage of a variety of coals. So BHL has that expertise, absolutely. Siemens boiler or Toshiba's boiler or any other Japanese Hitachi's boiler, for example, they actually have that experience. Whatever we are telling in here, that how variable the nature of the problem is, it is understood very well by the boiler designers, the more established ones, and BHL is no exception. So the point that I was trying to make yesterday was that if you switch on from a coal based in Jharia coal mine to another part of the world or another one, the first thing that they will ask, give me the composition. Volatiles, I mean the proximate, the ultimate, the ash analysis. If they see that it is all within their experience database, they will go ahead. If they see something completely out of the ordinary, they will ask for more information. In fact, when I was involved with the Angul plant, National Nalco's plant, the one of the bidders, 3 bidders, they actually took a substantial quantity of coal to test it before they put their tender, before they put their bids, sorry. So that's what they do. So all this information that I am churning out through my presentation, they seem complicated, but this is bread and butter to those people. They know it. So the other thing that came to my mind yesterday as I was talking to one of my research fellows, the way I have structured this presentation is I am keeping it at a high level, and then as I get your questions, I try to go into as much depth as I can within my available expertise. But I try to say things what are normally not available in the textbooks. So that's what I am. That's why you are seeing what you are seeing. But I could have easily given you an exercise on equilibrium calculations, gas composition calculations, which is all readily available in the textbook. I don't think it will be worthwhile all that much. So in case you are wondering why it is going into this type of directions, is purely because what I think from my age, and you can see how old I am, what I think is useful from the practical point of view. And you all are researchers. You will be going into the depth of research and you'll be knowing everything, but it is the high level implications that's very, very important to appreciate. So that's why I'm putting what I'm putting. Okay, so here, so the characterization of the ash, once you have done it, if you still see that nothing has been satisfied, it's not giving you a satisfactory understanding or explanation, then the next thing is to go for pilot plant trials, essentially by trial and error. Simply because if the coal is so much different from everything else that you have experienced before, under those sort of scenario, there is no other avenues than to go for pilot plant trials. That's why in many places you will see pilot plants. That's why they exist. But in order to run the pilot plant, you need engineering expertise. And then more importantly, in order to explain what you get in the form of experimental results in situ and ex situ analysis, that's what needs the sort of chemistry-based experience. Okay? Analytical, the information on how the analytical instruments can be better used to give you the answers to the questions that you are looking for. So so pilot plant was staying in the theme of fouling and slagging. Pilot plant trials are mostly used for fouling studies rather than slagging. It's simply because once it is slagged, it's gone. It's very, very difficult to clean the pilot plant. Fouling is easier to manage. Okay. And these problems can be coal specific, as I said. If it is the new coal that you are testing is completely different from anything that you have experienced before, no other course. So that's why I'm saying it is coal specific. And it can give you the direct test data. So for that particular coal, nothing more than that. But the plant configuration has to be similar to the actual boiler plant. Otherwise, the configuration, not the scale. The scale is also important. But if your actual boiler is going to be a tower type boiler, for example, Alstom used to give tower type boiler design. The boilers, the configurations of the boilers that I showed yesterday, if you can recall, it's a 2-pass with a neck in there to give you very high velocity at that neck, so as the majority of the fouling are dislodged. But there are other boilers for particular certain types of coal. The vendors give you tower type, straight, very tall. So if your pilot plant is of one type and your actual boiler is another type, it's a meaningless exercise, the pilot plant trial. So that's what I mean by the third bullet point. But the beauty of this pilot plant trial is that it can capture the time-specific effects on slagging and fouling, not so much slagging, hopefully. And these are difficult to assess from the laboratory trials, because in the laboratory you may have only this big rig, but in the pilot plant is this big. It's not easy to get exactly the same type of data from a laboratory one, which can be comparable to the pilot plant. Difficult, not impossible. So yesterday we talked a little bit about this. Okay, it's good to know all these problems, they exist, and how to analyze, etc. So what are the mitigation means in the real life, in the real plant? One is online cleaning, and by far this is the most used ones, so that the problem never gets out of hand. Okay. And then the location of the soot blowers and the wall blowers decided at the design stage based on the design call. So that's what the boiler manufacturers want right at the beginning. Okay, tell me about your call, and then we will decide how we will design it. We will decide where we will be putting the fixed wall blowers and the retractable wall blowers. We change in coal quality over time, the 1, 2, 3, 4, fourth bullet point. Soot blower location, frequency of blowing, and the time may need to be optimized. So that's common sense. Can be done in synchronization with heat flux measurements at dedicated locations. And sometimes you may need to redistribute the flow. If you see that the problem is getting out of hand and nothing can be done experimentally, go to the modeling stage, see what the CFD modelers are telling you about the gas flow patterns, which I said yesterday that it does affect, and accordingly redistribute it. But then again, CFD is a CFD. It's a prediction is a prediction. The prediction is based on all the assumptions that you use in your simulation. If your assumption is not practical, then your predicted results will not be practical either, right? So you really need to be very, very clear in your assumptions, and that's where a close cooperation between the modelers and the experimentalists or the operators are absolutely necessary. Doesn't happen all that often in the real world. The operators think the modelers are useless individuals, don't know anything other than running something on a computer and developing. I have even heard modelers, experimentalists, operators saying, oh, CFD, yeah, colorful figures and diagrams. So that's it. But they have to understand that there is a need for complementary expertise to come together. So if you know both, a bit of both, then your life will be a lot easier. So no one can fool you with a CFD result, or no one can fool you with an overinflated experimental or the real life problem, operational problem. You can say that, don't tell me all this rubbish. I know it is what it should be. It doesn't make sense to me. To tell me the truth. Then the next one, which I have deliberately separated from the first block, is the cold cleaning stroke blending. So this is something that we actually specified to one of the companies in Thailand. As they were moving from one mine to the other, their coal became a very high sulfur coal. Whereas the boiler, which was only barely 20 years old, so still significant life left in it, was designed for non-sulfur, very low sulfur coals. And they were having tremendous problems. So coal cleaning, either to get rid of some of the problematic species or blending it so as to bring the property with closer to the design coal, is often one strategy. But it's easier said than done, because blending is a physical event. You take something from here, something from there, mix them. That's physical. It's not same as the chemical. It's not chemically homogeneous, really, right? So even if it is blending, one has to be very, very clear as to how the blended coal may behave, so that its performance will be predictable. But sometimes it is not. And the second bullet point is only after electron microscopy analysis of the coal ash, efficacy of coal cleaning can be assessed. Coal cleaning is very very energy intensive, water intensive. So it only has to be done after very, very careful thought through process. Cleaning and washing can still be an expensive option, but at the very least, laboratory trials is required. And the 1, 2, 3, 4, 5, 4. Sorry, blending means a better understanding of the nature of slagging and fouling is required. As I said, blending is a physical mix, but coal is a chemical substance. And two physical mixes doesn't make a chemically homogeneous substance. Never. To justify blending, laboratory trials are absolutely essential. And I think no one will do it anyway, just purely blending. The majority of the large power generating companies, they will have access to either in-house or other institutions' laboratory trials, laboratory setups, or bench scale setups, so we can do it. And the last one is the use of additives. Only tried in laboratory studies, additives can bring in new sets of problems. I don't believe in that at all. I have put it in there because I see enormous number of papers published which will never see the light of application for a single minute. But people do it because it's easy to do, very fancied, and you can publish. So it's not practically useful. So I still put it there because you'll see it. Okay, any question before I go to the next one? Sorry? Good question. Can anyone start on that? So what's the purpose of the additive? That's a clue. To reduce fouling or slagging. So something that I said yesterday and something that I also said today a little bit. Yes, that's right. So you will select your additive in such a way that the proportion of those two go up, other ones proportionally go down. Excellent. I'll give you a copy of my drawing book tomorrow. Very good. So you will see that majority of the cases, the additives are actually clay, which are aluminosilicates. See that. So what topic you were working on, you said? Oh, that's good. Very good. Very good. I'm impressed. Any other questions? So the additives, the problem, though there are problems though. Practical problems. Aluminosilicates are very heavy compounds. As I said, alumina is about 3.7. Silica is about 2.5, so depending on the exact one, it's somewhere in between, right? The specific gravity of it. And then coal is what? 0.8? Less than 1, right? So these two are very, very different as far as handling is concerned. So if you put additives, first question is how much? You can calculate it. Then the question is, how will you mix them? Even if you can sort it out. Then the thing is, you're mixing it in the hopper far away from where the boiler is, maybe 20, 30 meters. Will there be any density-based segregation happening in between? If that happens, then the alumina silicates will go this way, coal will continue in its merry way. So the problems will still be the same. So that's why I don't believe in it. I mean, you can do fantastic work in the laboratory in this sort of rigs because they will be well behaved, but in the practical one, give it a toss. But good to know. And slugging, etc. Let's now shift our focus away to fluidized beds, because everything that we have discussed so far has centered around PF-fired furnaces, pulverized coal-fired furnaces. Pulverized coal-fired furnaces, I have said that the particle size is very fine, 10 to 100 micron typically, but that comes at a cost, because you have to grind it to that size, and there is a milling cost depending on the type of the coal. So from that point of view, alone, fluidized beds can be attractive. I shouldn't have used the word fluid. It's scientifically incorrect. It should be fluidized bed. So fluidized bed use extraneous bed material such as sand, silica or alumina, etc. Why? I will come to that later. Temperatures are much more benign, about 900 Celsius, limited by bed agglomeration. So what limits the temperature of the bed is the bed agglomeration problem, not slagging or fouling, but we will see examples of what agglomeration means. Slagging is decidedly absent because there is no flame and there is no high temperature, 1500 degrees centigrade temperature near the burner zone, so that there is no slagging. But the liquids can still form, but we'll come to that. But a new set of problems, bed agglomeration, appear in fluidized bed. So this is one of the schematic of a fluidized bed combustion pilot plant, the first one in Australia that I had the opportunity to commission and then run it over a substantial period of time. It's not a huge one, it's only 100 kilograms per hour coal feed. So what it is that this is the main combustor, so it's about just around 7.5, 7.2 meters tall. The internal diameter is 450 millimeters. Then it has a single cyclone. Okay, let's come to this way. We have the coal feeder, we have the additive feeders if necessary. I'm not talking about additives as in PF, here it is different. Then the cyclone separates the particles, unconverted carbon, etc., from the gases and puts them back here in an external heat exchanger, which consists of two chambers. In one, the particles drop and they are kept fluidized here, and then as their level builds up, they are fluidized state, they then overflow into this, because they are hot, we extract heat. That's why it is called external heat exchanger. So these samples are cooled here, solids, and then they are brought back with the help of this valve, or with the help of this pipe, which is called L valve, back into the combustor. There are different ways of doing it. Some people use what we call the loop seal. Some people use L valve. Here it is because it's of L shape. Some people use J valve because it's J shape. All sorts of things. Let's not go into that. Professor Shah may be talking about it a little bit. But this is what it is. This is built by Largi for the the Electricity Trust of South Australia, a government owned utility, and they got privatized, and they said, we are not going to commission it, we don't have the money. So they gave it to us, brand new plant at $1. So we got everything. South Australia. So I was the fortunate guy to be called in to commission it. Very fortunate actually, because I relish this sort of problems. So it's a big tool, big toy. Anyway, so then the cyclone, the gases then go to the convection sections where the gas is like your economizers in PF station. And then you have every point, you have the catchers for the particles. Then you have the air heater here, it cools the gas further. And then the flue gas then goes into the 3 flue gas coolers in series. Then it goes to a bag filter, and eventually it goes to the stack outside the building. And then we had electric air heater and blah, blah, blah. It was internally it was refractory lined, so you need to heat it up using natural gas. It took about 4 hours to heat it, and then cold feed came through from this hopper. So we were loading 1 ton, 2 ton bulk bags all the time. And if necessary, when we are using high sulfur coal, so we used to put the additives in there to capture the sulfur inside the bed. That's why these additive feeders are there, and also for other purposes. So we'll come to that. So this is where the major focus was, or major focus of my presentation will be. We'll not be talking anything much about this at all. Combustion. So gasifier, I will talk in the show it in the gasifier lecture. So this was the circulating fluidized bed combustor, because everything was circulated, everything. So establishing the circulation, it took us about 4 months. It's a lot of sweat and excitement and disappointment, etc. Establishing, knowing knowing how to establish the circulation in such a rig is a challenge often, because theories are theories, practices are different. So anyway, and then we had also primary air primary air and secondary air feeding. So secondary air at the freeboard, primary air somewhere here, which we haven't shown. And this is the photograph of the main combustor, if you like. That's the main combustor, and on the other side is the cyclones, etc. And what else? Yeah, the cyclone is there, and then we have the convection sections where the fouling deposits, the fouling, to interrogate the fouling, to examine the fouling, to assess the fouling. We had other probes, so we'll come to that later. So some of the coals that our power generating companies that gave us to test are these ones. These are coals from Victoria. These are brown coals. This is a char made by a company from this coal. And this is a coal from South Australia. All of those coals, 3 and 1, they are in their pristine state, they have a 60% water. And they said, we are not going to do any pre-drying, just do it. No pre-drying, just do. And if you look at the composition of it, important thing is the 4 to 5% hydrogen. And of course, the char will have all the volatile, majority of the volatiles gone from the char. That's why char has a lot less hydrogen compared to the coal. Nitrogen levels are more or less the same everywhere, always under 1%. Oxygen level about 26% in this one's. Char being char, volatile is gone, so oxygen also gone, that's why it's low. Ash, you see this very low ash. So supposed to be the dream fuel for combustion purposes, so little ash. Char has only 4% ash, this ash is in here. But then when you look at these two individuals, sodium and chlorine, this is extremely salty. 1% sodium is very, very high. So is chlorine, 0.49, 0.5 of 1%, very high. Then this, these are okay. Sulfur level, low, but this one is very high sulfur, 3.5, very high sulfur. Then we looked at the ash analysis. Low silica, moderate alumina, recipes for problem. Then iron oxide, very high here, recipe for problem. Sodium content, magnesium content are high. And then what else? Not much. So, and the iron content in this one, because it was made from this particular coal, that's why in these two iron content is very, very high. Okay. Sorry? Now, so this is the coal analysis. Yeah, yeah, yeah. Eh? So whenever you give, whenever you ask a boiler designer, this is what they will ask. Apart from approximate analysis, which I haven't shown here. So they will always ask approximate analysis, ultimate analysis, and your ash analysis. And they will then also, in our case, we were asked to test this because these have never been tested in in anything other than PF-fired boilers, and all of these coals are known to give very, very lot of problems in the PF-fired boilers, even though they are low ash, but fouling problems were tremendous. So the companies then asked us, can you test this in fluidized bed if the problems will be less or not? Huh? Say again? Yes, theoretically yes, but you know when you dry something, yesterday I talked about moisture reabsorption. So yes, you can do it, but then they become like sponge. So depending on how long have you kept them, they will start merrily sucking in moisture. That's why it is. Sir? I think they did it about 600, that company. Now, so it was made from this coal. That's why the iron contents are similar. That's why the iron contents in the ash analysis are similar. Right? Okay. So we decided, okay, our one objective was we will see how its combustion performance, whether it results in any unbound carbon or not in the fluidized bed, and then also if there are any problems, deposition problems, slagging, fouling, etc. Slagging unlikely. If so, how severe is the problem? All sorts of things. So no, ash analysis is done by different ways. It can be done by X-ray fluorescence, but it can also be done by ICP, inductively coupled plasma. So You can do it if you have access to an X-ray fluorescence instrument. You can do it by yourself. But the important thing is to know how it is actually done, because you can get all sorts of different results. So it's best to be done in a lab where they have used the X-ray fluorescence unit day in, day out, but also good to ask them, because not all coals can be equally efficiently or correctly be analyzed by X-ray fluorescence. So we looked at the simple things. We were asked, okay, run it continuously for 100 hours. So 7-day period. Typically, the performance guarantee test that companies give you for 100 hours. If it is on, then you'll get their money. You'll get your money. Otherwise, not. So that's why we embarked on 100 hours tests. So for this, all of these ones, we had no problems in running 120 hours, 130 hours also. We went straight in one go. So 3-shift operation, etc. But this is the one which gave us majority of the problems initially. We could not run it for more than 28 hours or 30 hours. Every time, 3 or 4 different tests, every time it will fail. After that amount of hours, bed agglomeration. So why it has failed? So then we realized, we sat down, we did all sorts of analysis. So what was happening? And the bed material there was sand. So we did bed materials with sand, bed materials with alumina, because we know that they are good ones. So at the bottom of the combustor, even though our bed material was about 350, 400 micron size, but this is the sort of agglomerates that we were forming when we tried to get the, when the tests failed at the 28, 30 hour mark. Every time it will fail exactly at the same time. So there must be a proper reason for it. It's not random. There is a proper reason for it. So we went out to investigate what was the reason. So what we did was then we took some of these samples and then subjected them to SEM in that order. So these are the individual sand particles, and see how they formed the agglomerates. So then we said, okay, let's go look at a higher magnification. We then looked at higher magnification onto the same particles around this area. That's why this particle is same as that. And then you can actually see how they are bonding with one another. This is agglomeration problem, not fouling, not slagging. Then we went deeper into it, and then we saw what exactly is in here at the interface, the glue, the sticky things. So we physically, we saw the morphology. Then comes the identifying what exactly is in the glue, what the glue is made up of. So we did a lot of those samples. We did the EDX. So when we looked at the individual particles, not exactly those ones I am showing in here, other particles from the same agglomerates, same batch of agglomerates. So this is the pristine actual sand particles, and over that there is a thin film of the gluey sticky substances forming. We then saw the other ones, everyone was having some sort of deposition around them. So it's not random, it's very, very regularly happening, homogeneous. and then we tried to see what exactly is this compound through EDX at that particular point. We could do other points as well, and then this is the composition. So we are seeing in here, this is a sodium, magnesium, calcium, iron containing compound, and also chlorine as well, over there. So this happened for only one coal, the coal which has a lot of chlorine in it, lot of sulfur in it. That's the one. So this is an example exactly of what I was discussing before, that what scanning electron microscopy can do to you when you try to investigate the reasons, try to get a mechanistic insight into the problems. But that's not all. Okay, and then we did a whole lot of analysis of these things, and then we realized, we found out that exactly what the glue was, what was bonding, what was the interface material on the between the two, which was actually over here, over in this region in here, even though it's a very thin film, but it's a glue at that temperature, it's sticky. So with the help of the EDX, then we determined its composition. We came out with a rough formula. We then came up from the literature or the library database. We saw what temperature it melts. We saw that it's actually melting around 900, 950 degrees Celsius. So even though our bed temperature was around 850 to 900 degrees, but that's the sort of temperature these are all forming and capturing the incoming particles gradually. And after 28 or 30 hours, it had captured so many particles into the agglomerate that the fluidization velocity that we are maintaining, about 3.5 meters per second circulating, it was not able to break those agglomerates up anymore. So what happened? The bed actually slumped. Now that's why it was happening around that sort of mark all the time. So we did it 3 times, we failed. Then we looked at it, we found out, okay, this is what is happening. Then we asked ourselves, can we prevent the formation of this sort of sticky substance? One is by bringing in additives, aluminosilicate clays, which will either dilute it so that it will not remain sticky anymore. That's one option. Or preferentially, if we have them, the clay materials, if we use them in such a fine particle size that it will provide lot of fine particle size, much smaller particle size compared to the bed materials themselves. So that the fine particles, in principle, they provide a very large specific surface area. The specific surface area means the meter square per gram. Okay. Finer particles, counterintuitive, but their meter square per gram is a lot higher than the larger particles. So one thing that we hypothesize is that if you use the fine particles, which have very high specific surface area, and because they are fine, they will be capturing these sticky materials preferentially on their surface. And because they are fine, much smaller compared to the bed material, they will be elutriated away from the bed, from the high temperature region in the bed, along with the sticky ones, keeping the bed materials relatively unscathed. So we tested that. We tested that, and then we could run that test for more than 100 hours. So we proved that particular concept in there. So it was that we said that, look, you can use clay. Clay is cheap, but a certain amount, and then we optimized it through the laboratory experiments and through one master student's 6 months worth of work, and then we gave the solution. But well before that, we then tested it, and then we could run it. So agglomeration is a phenomena which can be investigated very, very well. The reasons can be found out very well, and then based on those reasons, backed by the SEM analysis, etc., if you take the operational measures, then you can avoid, you can manage that problem. Sorry? Okay. So you have a fine particle, it's large particle, you have a fine particle. You are giving both of them the same velocity, which will elucidate first, the fine one, right? But the fine ones have larger specific surface area. So it will actually provide more surface to the sticky minerals coming out from the matrix of the coal. And those will be, and the finer particles can penetrate or get access to the sticky ones, sticky compounds, much faster than the larger ones. So they were collecting the sticky material on their surface, but because at the same time they were also finer, they were getting away, moving away from the bed. So the bed agglomeration could be managed that way. So that's one option that we suggested. We tried that. Everyone was happy, so we stopped at that point. But there could be other measures as well. Eventually they get cooled anyway. So eventually they get cooled anyway here in the heat exchanger. But then, because the heat exchanger is designed in such a way that the particles first come in here, and these clay minerals, clay materials are much larger in size. More they are denser in denser than the char particles coming in here. Char particles go in here, they come in there, and they can be taken out at regular intervals. What we haven't shown in here is that in as much as we have a bed media removal system in here, which we used to operate about once in 24 hours. So there was a valve. It's a plate valve actually, not rotary valve. You just open it, and then it drains part of the bed, not a lot of the bed, because then the temperature will drop substantially, and then you replenish same amount of ash, same amount of sand through the hopper. So that's what is done in normal fluidized, commercial fluidized bed anyway. So you drain part of the bed from time to time, and then you replenish the similar amount through the feeding system. Okay. So we did, eventually we postulated what was the reason. The reason was simply that in absence of the additive, when it was failing after the 30 hours mark, around the 30 hours mark, that there are volatile sticky compounds that were forming onto the bed materials, which should remain fluidized, but they cannot remain fluidized because they were becoming bonded to one another. So they are becoming very big, and eventually after a certain time they became so big that they could not be fluidized anymore. So that stopped it. So we found reasons, and then we we overcame it. So that was a success story. But as far as the fouling is concerned, at the back end of the plant, where we had the convection cooling section, we had these air-cooled probes. So on the left side, this is exactly what you will see the cooling. This mimics the cooling water tubes, if you like. But here the cooling medium is air. So inside the convection section, these tubes were there. Air was going in, keeping it cool, and then coming out from here, which we haven't shown. Sorry, actually, it's in here. So this is the clean one, and then this is what was the fouled sections, fouled probes. So if the fouling, as we showed yesterday during our fouling discussion, that initially in the direction of the gas flow there is a layer, and then it simply builds up. This is exactly what happens. So it's nothing extraordinary, similar in nature. The following problem is, but these, if you don't clean them, then the heat transfer through it will be impeded. The trick is to know after how much time you will clean it with blowers, whatever the blower is, so that this can be cleaned online. So that's the other point that I made a few slides ago when we were in the final slide on ash deposition in PF furnaces, that online cleaning at regular intervals based on experience, based on the procedure given by the manufacturers. If you follow it, problems can be tackled, can be managed. So we looked at for our interest what these were consisting of through SEM-ADX. These are mostly sulfatic, so which is very well known. The sodium sulfates, calcium sulfates. These are low temperature solidification, low solidification temperatures, and they are forming on the ash particles. Those ash particles were forming in here. The air-cooled probe was kept at 600. The first batch was at 600, second batch was 550, third batch was 500. So that's how we were managing it. Exactly what happens in economizers section of a power station boiler, progressively lower and lower temperature. So this actually gave us a strategy for the soot blowing. We knew after how many hours it builds up to such a level that it warrants cleaning. So that's the information that you know for soot blowing purposes, that after that many hours you will have to employ the soot blowing. Obviously, you will not do the soot blowing every minute. Soot blowing reduces the temperature. So you will do the soot blowing only for 2, 3, 4 minutes at best in one go. So the point that we did was, a point that we tried to make was from this, and the point that I'm trying to make to all of you is that here is a pilot plant operation, very large, reasonably large, had problems. We investigated it with scientific instruments backed up by very good scientific knowledge. And then we came up with the strategy, we implemented it, and it worked well. So the message is, there is no shortcut to success. There is no point trying to bypass the fundamental science. That doesn't work. I mean, it takes very long time. And all the tools are available. Predictive softwares, thermodynamic calculations, electron microscopy, everything is available. So as much as you know this, you will be able to come up with strategies for solving all sorts of problems that you will encounter in coal or biomass fired systems. So this, for the time being, concludes our combustion ash deposition one. I will move to the fundamentals of gasification, and then I will move into the gasification pilot plant experience, viscosity things, different types of gasifiers, and my experience running fluidized bed gasifier and entrained flow gasifiers now. And then the hot gas cleanup, possibly that will be tomorrow, gas cleanup business, and few other things that I am taking note of the questions that you are asking, and maybe a few slides in a separate shorter module towards the end of the week or early next week. But for the time being, that's as much as I wanted to tell you about combustion. So before I move to the next module, any questions from anyone? Yeah. No, it's because so limestone is calcium carbonate, and as soon as it gets inside the fluidized bed, operated say 850 or 900, at 800 degrees, limestone breaks down to calcium oxide and carbon dioxide. And that's what happens in cement mills anyway. That calcium oxide coming from the calcium carbonate or limestone or even dolomite, I mean, in fact, I haven't spoken about this 3.5% sulfur containing coal, we actually had to use dolomite for sulfur capture. But that's not what I haven't mentioned here at all. The dolomite actually also helped in agglomeration, alleviating agglomeration. Anyway, what will happen is the calcium oxide will not stay in the bed. Calcium oxide is very fine. Have you seen cement? Cement is extremely fine. So calcium oxide is very fine. So it captures it, and unless it is fine, it's not going to react with sulfur dioxide. It will take a very long time to react with sulfur dioxide to form calcium sulfate. But because of its size, it goes away from the bed. So bed agglomeration, calcium oxide, no, it will not contribute. Where it will contribute is in the here, because they will go and get a nice cool place to settle. And that's why I have said in here that when we analyze this by SCM EDX, these are mostly sulfatic. Why? Because of that. So what happened? This is a good question though. Yesterday, if you can recall, I said that sulfur in the coal exists in 3 different forms, right? Organic sulfur, inorganic, pyritic. Pyritic in some coals, not much, predominantly organic. So it's the organic sulfur which gives rise to sulfur dioxide, which you need to capture by calcium oxide, limestone, dolomite, etc. Dolomite, by the way, is a mix of calcium carbonate and magnesium carbonate. Okay? And magnesium carbonate also breaks down to magnesium oxide and captures the sulfur dioxide as magnesium sulfate, not to the same extent as calcium oxide capturing it as calcium sulfate. Anyway, so yeah. So the point I am trying to make is, it's the organic sulfur which gives rise to sulfur dioxide. That's captured by the calcium oxide as calcium sulfate, becomes gypsum, good thing to separate and then sell. But there is the inorganic sulfur that, as I said yesterday, is inorganically bonded to the coal matrix with the other minerals, calcium, magnesium, other things, iron, etc. So that part of the sulfur doesn't go there. It stays in the bed. So that can contribute to the bed agglomeration if you have too much of inorganic sulfur. But then again, it depends whether to what that inorganic sulfur is bonded to. So again, the thing is, you really need to know your coal very, very well. And that's why you need to know the ash analysis in addition to ultimate analysis and proximate analysis, and sometimes you need to know the minerals association in the coals as well. But there are ways to do it. So if you take a coal particle, subject it to SCM, you can, and if you properly prepare it, you can actually see the distinct mineral deposits inside the coal particle. So the minerals are not necessarily spread everywhere. If you take this coal particle, for example, some of the minerals may be here, some there, etc. So that will, and if there are a lot of inorganically bonded sulfur, then that will stay with the minerals, that will stay with the ash, that will stay mostly in the bed. Part of it may get elutriated, but For that inorganic sulfur, you will not need to supply any limestone, because that is captured by the other elements inside the coal. Right? Have I answered your question? Any other question? Okay, so it's not just aluminum oxide or silica. If they were the main ones, there will be not a problem. Same thing, the sodium, calcium, magnesium, iron, they're combined. So in some cases, in this case, for example, it was sodium sulfate, because we had so much inorganically bonded sodium sulfur there. It was the sodium sulfur, and such high amount of sodium was in this coal, very salty coal. That was creating the problem. Further aggravating that was the chlorine in it, sodium chloride. The chlorine is associated with sodium inside the coal. It's not present as molecular chlorine. So, so what happens is, if you take a mix of sodium sulfate and sodium chlorine and look at its melting point, it's very, very low. So if you have sodium chlorine somehow present, it can be problematic. So therefore, for salty coals, sometimes the power generating companies, they wash it out, the chlorine, for one reason, to give less fouling. But of course, if chlorine stays there, it can go into the back end, and over a prolonged period of time, prolonged exposure, it will give you high temperature corrosion. These tubes will be eaten out. So again, the thing is, you really need to know your coal very, very well. Yeah, and another question. Caking. No, our coal was not caking at all. So caking is non-caking. If the coal is caking, yes, that's another good point. The manufacturers, also boiler manufacturers, they actually want to know, is it caking? If the caking coals means caking coal, they become like cake on heating, just like cake. Very, very difficult to handle. So none of our Australian coals are, these are all non-caking. Coking coals are different from thermal coals. Coking coals would be of the highest order. Right? So the deposition that happens is a function of the coal ash property, temperature, environment, and of course time. If you don't do any online cleaning, they sit idle, of course they will build up, and then it will create unmanageable problem. And I have given this if you look at the ash analysis, ultimate analysis, together with the sodium and chlorine, then you can easily say that this coal will not be problematic anyway. Temperature. So, for example, so we had thermocouples inside all of these probes. So if there is problem happening, deposition problem happening, then the temperature inside will gradually drop. Same thing that happens in the steam tubes in a PF-fired boiler. As more and more deposition occurs on them, it will impede the heat transfer from the flame to the liquid, to the fluid inside. In this case, it's air in PFI boiler is usually, not usually, it is water. So if you see a gradual drop in temperature of that water coming out, or the steam coming out, or steam not being fully saturated, then you know that there is a problem. So that's the main. Very easy to detect actually. In-bed thermocouples for the bed agglomeration problem. Not only in-bed thermocouples, there are also the pressure transducers are there. So if the pressure transducers are kept clean all the time, then if you see the pressure drops across the bed increasing, that means the bed is slumping. Agglomerates forming, therefore pressure drop increasing, therefore the bed is slumping, fluidization will not be happening. So temperature indication and pressure indication are really the key, and therefore maintaining them is also extremely important. So nothing, a plant can be built, but as I gave the analogy of your car, the car will only be as good as you like to have it remain good. If you don't properly maintain it, don't check oil and water and everything at regular intervals, it will start fouling. Plant is no different. So what I haven't shown in here, this is a schematic. This is not a P&I diagram. The location of the thermocouples. So you will have thermocouples at different levels, at different positions around its diameter. A combustor, not a combustor, a reactor has to be properly instrumented, otherwise nothing will happen, because you cannot see what's happening. Your eyes and ears of the combustor to you are its thermocouples and the pressure indicators, pressure transducers. So if there is a problem in the bed agglomeration problem, it can do two things. First, for the temperature indicators, the temperatures will swing vigorously, because if agglomerates form and block the tip of the thermocouples, then it will not show a steady temperature. It will either drop or it will increase significantly, and you can actually see on the screen in the control room, if you are connecting all the thermocouples, sending your signals to the control room, then you can actually see which thermocouple is misbehaving. So bed agglomeration, that's what it will do to the thermocouples. To the pressure transducers, is exactly the same thing. The pressure transducers will also give you completely unnatural signals. So the pressure drops will be very, very high, which will mean that you are having bed agglomeration problems. So that's in the bed. Fouling, as I mentioned before, foulings are easier to detect because tubes you can put in thermocouples inside. If the inside temperature drops, inside temperature of the fluid, whether that's air or water, if the temperature drops, then you know that fouling deposits are, fouling is building up, and temperature can only drop. So these two. So, I will start with the gasification then. So, we will go into the fundamental side of the things, not much of a calculations at all, and then we will gradually will go into the deeper of the discussions on gasification, but also feel free to ask anytime any questions. So, this some of you this may be familiar with you. In gasification, what happens is that you are not supplying it, you are starving it of oxygen, as simple as that. In combustor, you give it excess oxygen in the form of excess air. In the gasifier, you do it exactly the opposite thing. You do not give it enough oxygen, because if you give it too much oxygen, it will give you carbon dioxide, which you do not want. You want less of it. So say for example, this is a gasifier, this box is, and the source of fuel into it could be anything, as long as it is a hydrocarbon. Coal is a hydrocarbon, biomass is a hydrocarbon, petroleum coke is a hydrocarbon, liquid feed, solid feed, mix of liquid and two-phase feed, all possible. The gasifier designs are available, and we will talk about that after lunch. So, what the gasifier does is that you are giving it less oxygen, but sometimes you also give it steam, not always, and it gives you combustible constituents such as carbon monoxide and hydrogen. And we will come to that, but without going into too much of it for the time being, let us then see in here. So, it gives you a combustible gas in here, which then sometimes is cooled if you want to change the proportion of carbon monoxide and hydrogen. Then you use what we call a shift reactor, which means shifting the composition of the gas. That is why it is called shift reactor. Okay, shift reactor. So, essentially changing the composition of the, giving you more hydrogen, if you like. If more hydrogen, receiving more hydrogen is the important thing, important objective. But in order to do the shift reaction, you need to cool the gas, and we will discuss that later on as to why and how much is there a compromise between those two and all. And once you have done the shift reaction, if you have done it, then you can remove the sulfur and the CO2 from there. Again, we are not going into it for the time being. You can remove the hydrogen or may not remove the hydrogen. The gas can go straight into the gas turbine, runs on the principle of the Brayton cycle, those who know. At any temperature you want, typically 12, 13, 1400 these days, the I-class gas turbines, they are available at 1500 Celsius. Different types of gas turbines are available. Again, let us not go into it. And then the exhaust gas from the gas turbine goes into the Rankine cycle part of the steam cycle part of it in the through the heat recovery steam generator, HRSG, where you raise the steam and to the combined cycle of the Brayton and Rankine, then you get the total electrical output, higher output compared to either Rankine cycle or just Brayton cycle. So, that is basically it. And when you are cooling the gas, you can actually generate the steam, because if you are cooling the gas using indirectly by using water, it will generate steam. Part of that steam can be used in the system, and then the other part can go into the for the power generation if you want to. But for gasification, you need to supply the substoichiometric air. If you are running the gasifier at higher pressure, then you need to supply it pressurized oxygen. That can come from the air separation plant. and this is a very energy intensive operation. If you remind me, why is the battery low? So it's fine. Yeah, it should. It's on, right? Yeah. Nice. So it was not properly plugged. But anyway, because it's such an embarrassment if it always goes. So I will actually go into some of this in a lot more detail. So please remind me to go into those if I tend to forget. But anything else that comes to your mind, feel free to ask. In as much as I can answer, I will answer. Otherwise, tomorrow on the other ones. The important thing in here is that we are providing a lot less oxygen compared to combustor. And you can actually literally get any gas that you want in any proportion, carbon monoxide and hydrogen, in any proportion you want. And that has a distinct advantage, because if chemicals production is a focus, and it is becoming more and more of a focus rather than power, so coal gasification, then there is no substitute for gasification at all. So why? So okay. So shift reaction. So gas cooling is done for two reasons. One is to cool the gas. To separate the alkaline component from the gas, so that the alkali vapors from the gas do not go into the gas turbine. The gas turbine manufacturers are extremely conservative. They want a very low level of alkali in the gas. So you can cool the gas, condense out the alkali. That's one reason. If power generation through gas turbine is the focus, and gasifiers will have to use gas turbines if power generation is the focus. No escaping from that. Second reason is shift reaction. Shift reaction is CO plus steam giving you CO2 plus hydrogen. So it is 1 plus 1 going to 1 plus 1. So no change in the number of molecules, no effect of pressure. That's fine. But the thermodynamics is such that the forward direction, that means hydrogen production direction, is facilitated if temperature is low. So you need to cool the gas down. But of course, if you cool it too much, then the reaction rate will be so small that you will need a huge shift reactor. So it's a balance that eventually you have to try. It's not really a feedback loop. It's actually reusing part of the, during the cooling, if you can use part of the heat back in the system, that will be good for the system's efficiency. So it's not strictly, it's not a feedback loop. It's you are cooling the gas by water, generating steam in the process, using some of the steam for shift reaction, some of the steam, if required, for gasification. So gasification reaction, I think in the 2 slides from now, I will show what are the reactions. Steam reaction with carbon is one of those reactions. So sometimes you need steam, but steam has a different role, and I will spend a fair bit of time on that. Yeah. Sorry, which gases? Not SOx. So, because it is substoichiometric oxygen, so sulfur dioxide will not be present, but sulfur has to go somewhere. Sulfur goes in the form of hydrogen sulfide, H2S. But that is not bad, that you can capture the hydrogen sulfide later on and can get through the Claus unit, Claus reactors or Claus reactors, elemental sulfur, which you can sell. No, before the gas turbine. No, before the. So, if you want, so that is why I have put the line as a dotted line, optional. Correct. If your focus is hydrogen production, and that is, for example, is the project that we are advising on now, I am advising on now in Victoria. Hydrogen production is the focus, gas turbine is not. So, this part does not exist, it finishes there. So it depends on what is, that is the beauty, that is the flexibility of the gasification process, that you can literally get whatever you want, not just power, but chemicals also. Yeah. Not much. Gasification is one word, incomplete combustion is two words. Difficult. Gasification sounds nicer, but in okay. And the other thing is, incomplete combustion sometimes means the carbon not utilized. But in gasification, the purpose is to utilize all the carbon, so that you get 100% carbon conversion or close to it. So, these, I mean, there is an underlying connotation that incomplete combustion means something inefficient combustion, if you want to interpret it that way. But otherwise, I mean, technically same. You are starving the carbon of oxygen, so that it cannot go all the way to carbon dioxide, it can stop only to carbon monoxide. I mean, not 100% to carbon dioxide, it will still have to generate some carbon dioxide, because that is an exothermic reaction, and that exothermic heat, or the heat generated from the exothermic reaction, is absolutely necessary to sustain the reactions that produce carbon monoxide and hydrogen, which are all endothermic. So, there is an equilibrium eventually that is reached. So, we will come to that. Good. Good questions. Anything else? Yeah. So, if you have a high sulfur coal, you can get sulfur from, in fact, that is how sulfur, sometimes sulfur is produced from the, so petroleum for a coke, for example, has a lot of sulfur in it, petroleum coke. Gasified, you produce the hydrogen sulfide or carbonyl sulfide or both. If it is carbonyl sulfide, then you hydrolyze it to sulfur dioxide. Then in the Claus reactor, standard technology, you can go and buy from off the shelf, get elemental sulfur. It is actually done. So, that is an advantage, you are right. You have to. You have to. So, maybe I will give a reference to a calculation which is in the textbook, which shows how to calculate the equilibrium composition. So, just for your reading rather than wasting time in doing the calculation here. But answer to your question, yes, has to be. So, everything that is there inside the coal has to be accounted for, right? Okay. So I may come back to it later on. The first node, energy in the carbon in fuels, is to generate hydrogen from water and fuel. How much time have we got? 1 o'clock is fine. We stop. What time do you guys go for lunch? 1 o'clock is fine. Because I don't want to start a long discussion now. Maybe another 15 minutes. Okay, I'll do so. So I will not spend any time on this one right now, but please remind me later on, because I have the habit of going tangentially at times. Okay, so the beauty of gasification is that you can generate any product, number of products that you want. For that, the building block is, you see, you can gasify almost everything, from waste to coal to liquid residues and natural gas to petroleum-based feedstock, anything. And you can see so much variety of products. Electric power is just one of them, easiest one to do. So that's the beauty of it. But in all of those, the common, for making all of those products, the common ingredient is carbon monoxide and hydrogen. And you cannot get carbon monoxide unless you gasify it. So if you get too much of carbon dioxide, then it's a problem. I mean, still you can get from carbon dioxide some of these products, but carbon dioxide is a very stable molecule to break. Carbon monoxide and hydrogen, you can, in different ratios, you can use it to get any of these products. And how you can get different ratios of carbon monoxide and hydrogen? By the shift reactor. So if you just gasify, it will give you certain amount of carbon monoxide and hydrogen, and of course some hydrocarbons apart from carbon dioxide. But not that amount of carbon monoxide and hydrogen may not be the right composition to any of those, or maybe just for one of those. So for example, for methanol, you need 1:3. Okay. For some other reactions, you may need 1:4, carbon monoxide and hydrogen, I mean. So you need to increase the proportion of hydrogen. And how can you do it? Through the shift reactor. You can get the hydrogen from the shift reactor. The question is, in the shift reactor, coal has only 4–5% hydrogen to start with, right? That's what we have said right at the beginning. So if you want more hydrogen after gasification, where will it come from? Because coal has only 4% hydrogen. It comes from, that's why I put this comment, it actually comes from steam. So when people say, you will read it everywhere, hydrogen production from coal gasification, actually what they mean is, or people sometimes don't understand, is that you are actually breaking the hydrogen molecule. You are breaking the water bond, the bond there, by using the energy scavenged from none other than carbon. To break the bond in water molecule to hydrogen and then oxygen, you need energy. That energy will come from where? From here, from this carbon, essentially. And that carbon has come in the form of CO from the gasifier. You are giving extraneous water steam here, and that's giving you the hydrogen. So, coal gasification giving hydrogen, actually yes, only to some extent. The majority of the hydrogen comes from the shift reactor. So, the yeah. Then if you give more than stoichiometric water vapor, it will go out as water vapor because it's excess. So, so it will not get any more than what you can get based on thermodynamics. So, CO plus 2H2O, for example, will become CO2 plus H2 or CO2 plus H2 plus H2O. So, that's what we have. Yeah. No. No. The maximum amount of hydrogen that you can get will depend on the shift reaction, and therefore and that will depend on how much CO you have been able to produce from the gasifier. There you can make temperature adjustment to get more CO, less CO2. But at the end of the day though, in the gasifier you have to produce certain amount of CO2 because that supplies the heat. That reaction, carbon plus oxygen giving you carbon dioxide, that supplies just enough heat to give you the carbon monoxide, to give you the to sustain the endothermic reactions, which I will show later on. Yeah. Correct. True. So, absolutely no. Right. So, you can get a maximum amount of CO from the gasifier depending on the temperature that you are running it. Of course, if you run the gasifier at a higher temperature, means you will be producing more CO2 to generating more heat. What that will do is that will drop the CO, right? Because the carbon is going towards CO2, not towards CO. So, technically, you will be better off to run the gasifier at lower temperature, so that CO is maximized and the reaction does not need much heat. But the thing then is, if you run it too low a temperature, lot of the carbon will remain unconverted. So, there is a balance. You need to run it at a temperature, so that all the carbons are converted somehow, and hopefully converted mostly to CO and less to CO2, just enough to supply the heat, right. So, there is the balance. So, this all can easily come from simple thermodynamic calculations. Put it in Aspen Plus, or you can do your own calculations, as I was telling, run a simple macro, run it in Excel, or in a lot of online tools are available these days. You can actually literally, you can put in the temperature and your coal composition, and then as a function of temperature, you can see how much CO, CO2 and hydrogen, etc. you can get. But the point I am making is, you can get only that much hydrogen from gasification, which exists in the coal to start with. In order to get more hydrogen than that, you have to rely on this separate reactor. even there, how much hydrogen you will get, additional hydrogen you will get, will rely on how much you are getting in it from in the first instance from the gasifier. That itself is related to the temperature of the gasifier. So, these are all to some extent interrelated. So, you are right. So, your question is, some moisture is coming from the gasifier, some moisture is coming from the gasifier because of the moisture present, some water, some steam is coming from the gasifier because of the moisture present in the coal. Absolutely right, but it is only small amount, because we want to feed a dry coal inside the gasifier for all sorts of different reasons, for energy conservation reasons. If you put in, if you have too much moisture in the coal going into the gasifier, then sometimes feeding of it is difficult, and therefore, you have to limit. And that's a separate discussion. So, please remind me to talk about that. That's another fascinating discussion which I wasn't intending to. So, remind me of that around 4 p.m. Okay, that's around that time I will be going into the practicalities. Yeah, in this instance, in the scheme that I have shown, not quite external, because we have to cool the gas. By cooling the gas, we are generating the steam. Some of that steam can go into the system. So, externally, what you are providing is only the boiler feed water, the feed water, and then once it goes, so in that sense it is external water, but steam generated internally. Correct. Correct. You can, and that is the point that I was making in response to the question from Dr. Dave, is that you only can do it to a certain extent. So, you can only control the CO2 ratio coming out of the gasifier by controlling the temperature. You can get higher CO by lowering the temperature, but only so much, because if you lower the temperature too much, then the carbon will come out as carbon. It will remain unconverted. You will need to provide certain amount of temperature to it anyway. So, there is a limited degree of leverage that you can apply, only limited. But yes, theoretically, yes. Not always, depends on the temperature, not always. Yes, it can be done, but this is actually one of the points that was raised by the sponsors of the project that we are advising us to advise. The problem there is, if you spray it inside, the steam will be, say that you are running the gasifier at 1000 degrees. Steam cannot come at 1000 degrees. That's practically impossible. Steam can come at, say, 250. The upper water only. So, what will happen is, then you have to raise that entire amount of water to 1000 degrees, the gasification temperature. Yeah. So, so let us give an example. 15 bar, the saturation temperature is about 220 or something. So say you put the water at 215 degrees at 15 bar. So that water then has to become saturated steam to whatever temperature, and then it has to reach all the way to the gasification temperature. Here, outside. But if you want to do it inside, yeah, that's what is usually the case. No, not sprinkled water. Usually you do it separately. Because if you sprinkle, spray water inside the gas will become saturated in water vapor. So the gas will now have hydrogen, CO2, and the sprayed water vapor, which you don't want. So it's better to do it indirectly. Where? In the shift reactor? Yeah. So around 300 or so. No, you can, okay. You can put steam at any temperature you like. If you put it at a high temperature, say 450, 500 degree, etc., the conversion in the shift reaction will not be 100%. Because the purpose of the shift reactor, it's a catalyzed reaction. So therefore, you cannot go to a very high temperature, number one, because the catalyst will not function. Number two is if the temperature is very high, the conversion of the CO and the steam to carbon dioxide and hydrogen will not be 100%. So there will be a lot of unconverted CO and water vapor steam will remain, which you don't want. That's another disadvantage. So if you look at the shift reaction, which is actually a reversible reaction, the forward reaction, I should have shown reversible sign in here. If temperature increases, the reverse reaction becomes prominent. So you will be getting a lot of unconverted CO2. But if temperature decreases, the reaction will proceed in the forward direction, which means you will get a lot of hydrogen. Problem with too low a temperature is it is a kinetic process, so the rate will slow. And if rate slows, then what will happen? The reactor has to be very, very long, very large. So there is a delicate balance, and therefore, where is the balance? Around 300. That's more or less universally accepted these days. That you get just enough rate and just enough conversion. Oh, okay. So you have raised another Pandora's box, opened Pandora's box. I was intending to open it after lunch. Yes, that's right. Okay, good, very good. I'm actually quite impressed. I'm enthused because my students don't ask this sort of questions. Should have brought them here. Okay, so the gasifier, you know, in one of the few slides later, I will show. In the gasifier, what happens? Some amount of drying will happen. Some amount of drying, depending on what the moisture content is going with the coal, 2, 3, 4%, whatever. Then pyrolysis. Pyrolysis will produce methane, right? And at those sort of temperatures, you won't get much above methane. So C2, C3, C4, etc., very, very low. So the methane will be coming predominantly from pyrolysis process. That is the first step before the gasification, char gasification that takes place. So that methane will remain in this system anyway. And I haven't shown it. I was going to show it later anyway. That methane, nothing will happen to this methane in the shift reactor. It will simply go out. But if gas turbine, the power generation is your focus, not a problem. The methane will burn brilliantly, right? It's not a problem. Problem is, if chemicals production is your focus, and therefore you need carbon monoxide and hydrogen, then what do you do with this methane? That's the challenge. Because in all of these reactions, in here, for all of these products, you don't need methane. So some of the coals which can produce a lot of methane are obnoxious, but there are ways to tackle that methane as well. It comes at some cost. So we'll talk about that too. Unless you cool it down all the way to, and then you apply membranes. But then again, cooling down means exergy loss. However you look at it, okay, you cannot avoid certain amount of exergy loss, right? No, because yesterday I said pyrolysis starts quite early, right? In the pyrolysis process, majority of the methane is released. So methane will be released quite early, well before gasification starts, 400-500 degrees. And gasification doesn't start until 800 anyway. So methane is a fact of life. It will remain all the way through, whether you like it or don't like it. Only way you can avoid it if you use char in the gasifier, because then you have taken the methane out from the pyrolyzer. But that's a separate reaction scheme, separate set of problems that you can do. So technically that way you can do it, but no one does it that way. So people can do live. Fortunately though, the methane is not much more than 3 or 4% of the total, volumetrically, in the total gas coming out of the gasifier. Never. I mean, unless you are running the gasifier at a very high pressure, where extra methane can be generated from carbon and hydrogen reaction, but that doesn't happen at all below 25 bar. You will require 30 bar, 50 bar, upwards of that. So methane, extra methane will never be generated. Only methane will be coming mainly from the pyrolysis source. No. So you have, say you have mixed, you have a cylinder, gas cylinder, where you have asked Air Liquide or BOC or whoever supplying the gas, give me a mix of methane and hydrogen and carbon monoxide. Start playing with it, supplying inside a reactor some amount of oxygen, see which one comes out first, which one comes out unscathed, and then which one gets scavenges all the oxygen first. Methane, nothing will happen unless you make it force it to happen. There are ways to convert the methane together with the carbon dioxide, but it will require a lot of catalysts. The Sabatier reaction, for example, is one example through which you can convert the methane. And there is a way to, there is an advantage to separately convert the methane, because eventually to hydrogen through catalytic processes, because methane sells at about $100 or so per kilogram. Hydrogen is about $1,000. So there is an incentive to do it, but it has to be pure methane coming from natural gas, for example. Coal gas, petroleum gasifier gas, you get moderate pressures, 25 bar or so, below 30 bar, you will be barely getting 4% methane, not enough to do those sort of things. No, there are they are utilized to some extent, but that changes the dynamics, that changes the efficiency of the shift reaction and any other processes. Oh, okay. So the hydrogen that comes directly from the coal, it comes during the pyrolysis stage. So by 600 degrees or so, well before the gasification starts, hydrogen, methane from the coal itself will be evolving anyway. So when you gasify coal, what happens is, and I was going to go into the fourth slide and we'll be discussing that there, the coal gets dried. So what remains is moisture free coal. Then it gets devolatilized or pyrolyzed. That releases some amount of CO, CO2, methane and hydrogen. What remains is carbon or char as we call it. That char then goes into reacting with the substoichiometric oxygen. Whatever oxygen has remained after competition with the hydrogen that has been released, after competition with methane that has been released, that oxygen then is available for char gasification. So there is a subtlety in there. If you supply all the substoichiometric air right at the bottom, then the hydrogen and the methane and the carbon monoxide released from the pyrolysis stage will nicely see good food in the form of oxygen near itself. So that is why you have the secondary oxygen, tertiary oxygen, etc. So that it is there where the char is. And when I talk about the different types of gasifiers, I will explain it there. So it's more complicated than what we can think. Where you introduce the oxygen is extremely important, because if you are introducing oxygen at such a high temperature, near where it sees only hydrogen and methane and CO, the poor carbon will have no chance of getting any oxygen. It will all be scavenged by these three molecules, right? So that's the gasifier design aspect. So we'll come to that. Not separated directly, not separated at the gasifier at all, after cooling and all. Gas separation at high temperature is an unfinished, unresolved business. If you want to, membrane. That's the best. What should be the? Of the gas after the gas cooler? You mean here? Whatever temperature you want to run the shift reactor at. Tar, okay. Tar is one of the hyped up facts by, career academics. I am also an academic, because tar opens up the possibility to write so many journal papers. If you can make tar, you can do it, use, no disrespect intended, I am in the same category. But tar is something which can be avoided. So, one of my gasification papers from the early 2000s, I have made it, tar generation was not a problem. I have been very, very polite because the papers will not get published, because papers are reviewed by the academics. So you cannot antagonize them. Anyway, tar is nothing but long chain hydrocarbons. Okay, CXHY, little bit of OZ. So if it's long chain, what do? You break the chains to shorter chains. How do you break them? Heat, either being in oxygen or being in steam. If you put steam in the gasifier, tar goes away. So don't believe a lot of the tar papers. Just the tarred with the brush of impractical vested interest people. And I say it on record because I have nothing to lose now at this stage of my career. That is not a problem. You will not hear of any problem of tar from gasifier developers, Mitsubishi, GE, you name it. They will not talk about tar. You can see who talks about tar. Anyway, any other questions? Now you can break it inside the gasifier. Because the tar doesn't exist as tar anymore. It's all converted to short chain hydrocarbons. So in fact, tar cracking is it can give you a lot of methane, and in fact, it can also give you hydrogen. So that's what happens. Only if you give it oxygen. No, so what are the long chain hydrocarbons? C15, 16, etc. These will all come down to the shortest possible chain, C1H4. Unless you give it oxygen. So in the gasifier, at the exit, oxygen is 0. Because all the oxygen, the little bit of oxygen that you have given to the gasifier and the substoichiometric oxygen has all been used up. No excess oxygen in the gasifier outlet. First of all, if you are doing the gasification at high temperature, there will be bare minimum tar. But if you do when is tar produced? Only when you are pyrolyzing, when the temperature is 500 or so, 400, 500, 300, etc. But in the gasifier, you don't have that temperature anymore. All on a sudden, the particles see very high temperature, whatever temperature you are running the gasifier, 900, 1000, 1100, 1200, etc. Right? So, but you can produce tar if that's the objective. In fact, one of the projects that we are doing in Tasmania at this point, they asked to deliberately produce tar. So we stayed in the pyrolysis zone. We stayed about 500 degrees, produced a lot of tar, liquid tar, and then convert it into other fuels. But gasifiers which run at high temperature, and low rank coals even lesser of a problem. Low rank coals are reactive gasification from the gasification perspective. So they are just enthusiastically waiting to react compared to the mature ones. Just like the young kids versus the oldies. The oldies are very conservative, not very, very resistant to change. The young people, you guys, you always want to embrace change. It's like, so tar gets cracked when you put in low rank coals. High rank coals is a problem. But why would you use too much of a high rank coal in gasifier?